Good morning, all of you. Good morning, sir.
Good morning, sir.
Our Honorable Vice Chancellor, sir, Professor J.P. Pandey, sir, has joined the session. So I like to welcome Honorable Vice Chancellor, sir, Professor J.P. Pandey, sir, uh, Vice Chancellor of Triple MUT Gorakhpur, and the Chief Guest of this function. Now I'd like to invite Professor Sriram, sir, Professor and Head, Civil Engineering Department, for the welcome address. Professor Sriram, sir.
So you are not audible.
Hello. Due to this some problem, now on behalf of the Civil Engineering Department, I welcome Professor J.P. Pandey, sir, Vice Chancellor Madan Mohan Malvi University of Technology, Gorakhpur, and faculty members of the Civil Engineering Department, and Professor M.L. Sharma, Professor in Seismic and Earthquake Engineering, IIT Roorkee, and the other these fellow delegates who are going to join this 5-day FDP program. And this 5D during these 5D days FDP programs, different topics will be covered related to the seismic, and these topics are basic knowledge of earthquake engineering, seismology and earthquake engineering, site investigation, ground improvement techniques, seismic microgeneration, and liquefaction of soil. As you all know that nowadays these high-rise buildings are being constructed throughout the India, and in this 60% of the India comes under these high seismic zones. So we require the knowledge of earthquake resistant design as well as this knowledge about the soil investigation also, because this is very important in comparison to the soil this earthquake resistant structure. If the foundation fail, every structure will be failed. So you have good knowledge about the liquefaction of soil and then ground improvement techniques. And I hope during these 5-day deliberation, this all experts that are from the different NITs and IIT, you will be benefited. And at the last, I again welcome you and thank you very much.
Thank you, Professor Sriram, sir. Now I'd like to give a introduction about this 5 days workshop on recent advances in earthquake engineering. The purpose of this program is to mainly provide the researcher with a basic understanding of earthquake engineering and geotechnical earthquake engineering. This faculty development program will be covering the understanding of seismology, earthquakes, ground motions, and soil and its site effects, and the characterization of soil and ground motion, seismic microzonation, and dynamic properties of the soil. All the sessions, approximate 14 sessions, are totally included in this FDP, and all the sessions will be taken by the eminent faculty members of the top institutions of the India, like IIT Roorkee, IIT BHU, Manit Bhopal, NIT Raipur, and CSIR, CBRI, Roorkee, and some industry experts also will be there. Approximate 100 and plus students and faculty members have been joined from the pan over India level, which includes from Andhra Pradesh, Assam, Bihar, Chhattisgarh, Delhi, Gujarat, Haryana, Jammu and Kashmir, Karnataka, Kerala, Madhya Pradesh, Maharashtra, Odisha, Rajasthan, Tamil Nadu, Telangana, Uttar Pradesh, Uttarakhand, and West Bengal. Uh, Now I'd like to request our Honorable Vice Chancellor, Sir, Professor J.P. Pandey, sir, for his blessing words.
Professor MS, Professor IIT Roorkee, Head of Department Civil Engineering, Dr. Sriram Chaurasia ji, all the faculty members of the Civil Engineering departments. I would like to first congratulate these coordinators and Department of Civil Engineering for organizing 5-day faculty development program on recent advances in earthquake engineering. That is sponsored by ATAL, that is AICTE Training and Learning Academy. These coordinators, Dr. Pradeep Mule and Mr. Rohit Kumar, they have done a very good job by initiating this 5-day FDP on this very important topic of civil engineering. As you all are known that this prediction of earthquake is a tedious job, and we are working on it so that we can have a prediction that this is the location, like falling of lightning. We are unable to locate the point where the lightning is going to be happen. But as far as this earthquake is there, we are having sort of technology, we are having sort of prediction methods so that we can have a prediction that this is the place where in the next 48 hours, next week, the earthquake will happen. All the experts will give different aspects of your earthquake and seismic engineering. But my request to all the experts is that, and along with this, all the participants who are connected with this 5-day FDP, as the coordinator is telling this, the participants are connected all across states, other states too, that we will have to focus our knowledge and our research using the modern tools available with us. There are so many modern tools, and probably the experts will have research in these modern tools also. That, for example, artificial intelligence, machine learning, fuzzy logic, data engineering, data mining. Basically, when you will go to locate the prediction for this earthquake or seismic zone, in the seismic zone, you will need all the data which is to be processed very thoroughly, very precisely. So my request to all the participants to use these modern techniques, although it is seems to be a computer oriented, but not like that. You can use the data analysis, big data analysis, analytics, and with these tools you can reach to a conclusion that this is the point and this is the time where this earthquake will fall in, and this will definitely give big boost to our disaster management capability. In any country, particularly in our country, we are facing a lot of problem in having a disaster management during these type of calamities. So definitely this after 5 day, our experts and this all the participants will come to a conclusion that we these are the line where we can start our research. These are the areas where we can focus our research so that we will come with some innovative outcomes for this advanced learning of earthquake engineering and earthquake science in these 5 day FDP. With these words, I'm again thankful for all the organizers who are organizing this 5 day FDP. And this is the initiation of civil engineering, particularly under the headship of Sri Ram Chaurasia. And he is also be congratulated for this because in this session they have started, I think this is the second FDP they have started. I think the first FDP in this session started by civil engineering. For this, all the faculty members of civil engineering are responsible, and definitely with these things, if they will go on carry on these rhythm and motivation, definitely in coming days the civil engineering department will come with so many innovative ideas. We can start startups, and we will focus our research students to come with the ideas, and we will give a platform. The university will provide a platform to nurture them, nurture their ideas to come for the industry purpose. With these words, thank you very much. Thank you.
Thank you, sir, for your kind blessing words, which really motivates us for this and these types of program for the organizations. Now, I'd like uh, my colleague, Dr. Pradeep Bhule, coordinator of this FDP, for the vote of thanks.
Yeah, good afternoon. Chief guest of the function, Professor J.P. Pandey sir, Honorable Vice Chancellor, Triple MUT Gorakhpur, Professor Shriram Chaurasia sir, Head of the Department and Convener of this FDP, and my colleague, Mr. Rohit Kumar, Assistant Professor and Coordinator of the function program, all the respected faculty members, uh, and dear participants. Thank you very much. Thank you for giving your presence in the inauguration function for AICT sponsored faculty development program on recent advances in earthquake engineering 20 to 24 September 2021 at Triple AMUT Gorakhpur through online mode. It is my privilege to propose the vote of thanks on the successful completion of this inauguration function. On behalf of Department of Civil Engineering and Organizing Committee, I express my deep gratitude to Professor J.P. Pandey sir, Chief Guest of the function, and Honorable Vice Chancellor sir, Triple MUT Gorakhpur, and Professor Sriram sir, Convener of this FDP program and Head of the Department, Civil Engineering Department. Uh, to my thanks to Registrar sir, my thanks to ATAL Academy, ATAL Training Learning Academy for the sponsorship and the funding for this M. And also thanks to all the deans, all the heads, and uh, last, I thanks to all the respected faculty members who joined us, and thank you very much for all the dear participants and uh, uh, dear resources person. Thank you very much. Jai Hind. Yes, thank you, sir. Thank you very much. Yes. Now we start our session one. Yeah. Professor Amel Sharma, sir.
Yeah, I'm here.
Yes, sir. Good afternoon, sir.
Good
Yes.
afternoon.
Yes, sir. And
Okay.
yes, let me introduce the Professor Amel Sharma. Professor Amel Sharma, sir, more than 36-year experience in teaching, research, and consultancy in the area of earthquake engineering. Presently, Professor Sharma is the Dean Planning and Finance at IIT Roorkee. He has been head earthquake engineering department during 2012 to 2016. Uh, Now the president in Indian Society of Earthquake Technology during 2014 to 2018, and the chairman of JE Advance for 2017, 18, and 19. Professor Sharma has uh, Professor Sharma has technical expert give the technical expert advice to more than 500 engineering sites in India as well as abroad, reading the seismic hazard and risk assessment. Professor Sharma plays the key role in seismic instrumentation around the dam and development of earthquake early warning system. He has actively associated with international programs, especially with Norway, Mexico, Taiwan, and Israel, for the disaster mitigation. Professor Sharma has awarded as AS Arya IIT Roorkee Disaster Prevent Award in 2012. He has fellow in Indian Society of Earthquake Technology and Indian Geotechnical Society and Indian Geophysical Physical Union. He has published more than 250 research papers in general international conferences and national conferences. Professor Sharma has guided 23 PhD, 23 PhD and 10 PhD are in progress. He has guided 72 MTech dissertations. He, he has also established a startup, namely Shri Seismological Instrument, under the Make in India and Atmanirbhar Bharat. Uh, Thank you very much, sir, for accept our invitation. Uh, uh, as a sir title is Engineering Seismology, and yes, sir.
Yes. So, Dr. Pradeep, should I now start the lecture?
Yes, sir.
Because we are already 12 minutes late.
Yes, sir. Sorry, sir, for delay.
Okay. So, I will just share my screen
Yes, sir.
and start the lecture directly. Thank you very much for inviting me to this. That teaching is one of the things which fascinates the teachers. So I would love to give the lecture on engineering seismology. And this is a starting point. Am I audible to all?
Yes, sir. Yes, sir. Order.
Okay. So,
Yes, yes,
yes, this is
yes,
the
sir.
starting point, and just the introduction to the earthquakes, because this course we will be using earthquakes everywhere as a physical source, as a ground motion to all of our buildings and design. So how to go for that? So for that you must understand about the earthquakes. Now, if you see in the past, this is one of the things which is other side of earthquakes, the damages, the casualties. And if you start in the last century, run of Kutch, more than 1,000. It's only because at that time the population was very less. In 2005, Kashmir earthquake, it was, I'm in a lecture. I'm in a lecture. So you can see a lot of damage. So earthquake damage is considered as one of the most important damages in natural hazards. This is one of the very important natural hazards which is affecting almost all parts of the earth. And as Dr. Pandey has also given you the idea, we are unable to predict it. And if we are unable to predict, then what has to be done is we have to study the earthquake deep and then use that knowledge to predict the ground motion, go for the probabilistic theories, get the ground motion, and use it for our future endeavors. This is just one of the slides just to show and remind you of, many damages and lots of damages in India and for that sake throughout the world. This is Bihar Nepal earthquake, more than 10,000 casualties, and it was an earthquake of around 8.1 magnitude. So with this background, let us just try to understand what the earthquakes are and how we study them. So the science which study the earthquakes is seismology. It's a branch of geophysics. Geophysics is nothing but the three-dimensional version of geology, because in geology you go to the two-dimensional version, and geophysics is the third dimension where you go deep inside the earth and in the third dimension. If you see the physics of the earth, if we can study from geodesy, geodynamics, geochemistry, geomagnetism, and seismology, including geology, mineralogy, hydrology, meteorology. So there are so many things that the physics of the earth, including seismology. So the difference here is that here we are using the use of the wave propagation and the elastic media. So that is part of the seismology. If we talk of artificial source, then it becomes seismics. In seismics, for going for petroleum prospecting or going for mineral prospecting, you just what you do, you detonate dynamite at a place and then record the observations at some distance, and just like your medical science, they use these wave propagation to map the things. Similarly, seismics, the elastic waves, they propagate and then they take with them the property of the medium, and then you map the medium. So that is seismics. So the difference between seismics and seismology is that here we are using the natural source, which is the earthquakes, and here we are using the artificial source. The seismology is also further divided into many parts. Observational seismology, where you are using the instruments and observe the data, deploy networks in the field. Then theoretical seismology, where we make use of the physics, all laws of physics. You know that once we consider the Earth as an elastic medium, the whole elastodynamic theory is available to us. And therefore, all the laws of the physics, whether that's a Hooke's law, whether the Newton's laws, whether it is Huygens principle or Snell's law, whatever these simple laws, they are readily available to know the propagation of the ground motion. But in this ground motion, strong ground motion is of specific use because of the damages to our built environment. And here comes the earthquake engineering. So this is more near to earthquake engineering. Then what is engineering seismology? Basically, engineering seismology is the gap between the science and the engineering. Whatever products the engineers wants to use, say as an earthquake engineer, you want to use a strong ground motion time history. That is a product of engineering seismology. You want to use what is the magnitude of the earthquake. That is the product of engineering seismology. you want to know what is blow you. I mean, that is a common thing in geotechnical engineering and seismology, because in seismology, the multispectral wave methods, MASW, okay, multiple analysis of the surface waves. So these are all parts of seismology. So that is more near to that. So what is there in engineering seismology? Causes of earthquakes, plate tectonics, instrumentation, data acquisition, medium characteristics, wave propagation, location and size of earthquake, seismicity interpretations, and whatever are the products which are between seismology and earthquake engineering, they are the part of engineering seismology. Now, Dr. Pradeep has given me a very, very wide topic of telling you about engineering seismology. And you know, it's a one semester course. So I was just thinking of what should I give to you. So then I thought, okay, I'll be giving some basic knowledge about the earthquakes, and then some of the questions you may like to ask, and I will be just going for those questions. Now, if we divide, want to know what is the sources. So there are two types of sources, earthquake sources. One are natural events and another are man-made events. So in natural events, tectonic earthquake. Tectonic is basically a Greek word. Okay, so I can use my pen also. So it's a Greek word, and it means it's a Greek word, and it means force. So whatever forces are there within the earth, it is because of that. So tectonic earthquakes, and they are more than 80%. Okay, so more than 80% of the earthquakes, they are tectonic earthquakes. So wherever you hear about the earthquakes, particularly in India, they are all tectonic earthquakes. Then comes the earthquakes which are volcanic earthquakes. Then the implosions, collapse. Then the oceanic microsis, which are very smaller one, and because of the oceanic noise. These are also known as earthquakes, but they are man-made earthquakes. Maybe some control event, explosions and cultural noise, or maybe induced triggered events, reservoir induced seismicity. Nowadays, it is very important. Mining tremors, fluid injection. What is going on in Punjab is they are injecting the fluid to take out the petroleum, and because of this, there are some earthquakes. Okay, these are the basic things. This is the earthquake source. This is the earthquake source. Oh, sorry. This one here, this is known as hypocenter, which is below the earth. At the surface of the earth is known as epicenter. And here, this is the observation point. So the distance within the earth is the hypocenter distance, and above the earth, it is the epicenter distance. So these are some of the terms which we may be using. So I thought that let me introduce them also. Then classification of earthquake is also one of the important things, because very often we are using these things like if whether they are within the plate or outside the plate. I will be telling you about the plate. They are called as interplate or intraplate. Based on magnitude, we call the earthquakes which are less than 3. We call them micro earthquake, intermediate earthquakes. Similarly, 5 to 6, we call them moderate earthquakes. 6 to 7, strong earthquake, major earthquakes. This is especially important, the great earthquakes. There are around 5 great earthquakes in India, and I will be telling you about these. then based on the distance, how far it is from you, if it is within 100 kilometers, then this is the local earthquake, we call that. And if it is between 100 and 1000 kilometers, we call this as regional earthquake. If it is more than 1000 kilometers, we call this as teleseismic. And we use it, very, very often. Shallow earthquakes, less than 30. Intermediate earthquakes between 30 to maybe 300. These are more than 300. There are many definitions. Sometimes we use 70, sometimes we use different authors have given different definitions for this. So if some earthquake has happened in Roorkee, I'll call that, and it is a magnitude 3, I'll call that as micro earthquake, local shallow. So there was a shallow local micro earthquake in Roorkee. So this kind of things I'm just introducing so that you know it. Now, what causes the earthquakes? And for this, you must know, set up your visualization for that kind of thing. I've taken some examples. Say, one of the examples is this. Run of Kutch earthquake. This was a magnitude 8 earthquake for which a bandh was created because it was a Muslim area. They called it as Allah Bandh for 25 kilometers long. And the down throw was 3 meters. So it means the earth has came down to 3 meters. Another is the March 26, 1872 earthquake, Owen Valley, California earthquake. Now here, parallel to Alabama Hills, around 15 kilometers long, it was 7 meters vertical and 4.8 meters horizontal displacement. So in this case, some of the portion has moved up and some of the portion has moved down along the fault. Then in Assam earthquake, Chedrang fault, 20 kilometers long in crystalline rocks. Sorry, this is rocks. Up through of 10.5 meters means that 20 kilometers of the fault was upthrown by 10 meters. Now you can understand the type of and the amount of energy released in that. Then the California earthquake, the San Francisco earthquake. This is very important earthquake. Oh my God, why it is changing? This is very important earthquake because the earthquake theory was based upon this. Okay, this was on San Andreas fault, and for 430 kilometers long, 6.3 meters was the slip along the fault. So it means that around 430 kilometers, this side and this side, the difference between the displacements was 6.3 meters. So, I mean, you can now visualize the kind of energy release in these earthquakes. March 27, this earthquake, southern Alaska, few hundred kilometers of crust, 13.5 meters uplift and 2.2 meters subsidence. So around 2 meters of hundreds of kilometer thrust was upthrown or downthrown. So it means that all of them, they are related to faults. So what we can say is that the immediate cause of earthquakes is faulting. Okay, that kind of faulting, maybe thrust, or maybe strike slip, or so if time permits, I will be showing you the examples. But what is causing the fault is the ultimate cause, and that is the plate tectonics. So before going to plate tectonics, I will just tell you the elastic rebound theory, and then we will just look at the plate tectonics, because in this lecture you will not be finding a very specific topic. I want to cover many of the topics which are related to earthquakes, and then you can understand the earthquakes better. Elastic rebound theory, in which the earthquake is nothing but a sudden and transient motion inside the earth. And what happens that if the force is applied on this, then up to some point, it will go like this. And after that, when the strength is more than the force is more than the strength, it will break. And that at that break, the earthquake will occur, and that is energy release, and that is called the earthquake. Okay, so the elastic rebound theory simply tells you that there is an energy accumulation, and that energy is accumulated until the strength of the material is crossed. And once the strength of the material is crossed, that there is a break, and then there is an energy release, and that energy release is nothing but the earthquake. Now I'll come to just little bit of the plate tectonics. This theory was given in 1915 and up to say 1930, this theory was not accepted. So Alfred Wegener, he gave a theory that there are plates, and there was one continent known as Pangaea, and from there the continents they split apart, and so, but that was not accepted until 1930. Then what happened in 1930? We have got many of the evidences, and those evidences includes, first was demonstration of ruggedness in the form of oceanic ridges, island arcs, trenches, and youthness of ocean floor. If you see the ocean floor, there are so many ridges, island arcs, from where they have come. So it means that something dynamic is there. Then confirmation of repeated reversals of earthquake magnetic field. This came during the Second World War. People, they were selling their ships, and suddenly they found that, okay, there is a magnetic reversal. And why there was a magnetic reversal? Because of the plate tectonics theory. Then the emergence of the seafloor spreading hypothesis in 1962. So that was also one of the evidence. Then precise documentation that world's earthquake and volcanic activity is concentrated along the oceanic trenches and submarine mountain ranges. Okay, so because of these evidences, we could know that there are plates, and these plates are lithospheric plates which move in different directions. So the Wegener theory was accepted, and then the plate tectonics was treated as one of the reasons for the earthquakes. Okay, and what are these tectonic plates? These tectonic plates are the crust and the uppermost mantle is rigid, forming a hard core shell which is known as lithosphere. So lithosphere, I mean, that is, it contains both the crust and the uppermost mantle also. Okay, so it means that if this is the crust and this is the mantle, then this portion, which is rigid, is the plate. Okay, and beneath the plate is the asthenosphere, which is lower rigidity. So what happens is it is of lower rigidity and high rigidity, very hard one is here, so it tries to float on this. Beneath the lithosphere lies the asthenosphere, a layer in which seismic velocities often decreases, suggesting lower rigidity. It is about 150 kilometer thick, although its upper and lower boundaries are not sharply defined. This weaker layer, yes. This weaker layer is thought to be partially molten. It may be able to flow over a long period of time like a viscous liquid or plastic solid in a way that depends on temperature and composition. The asthenosphere plays an important role in plate tectonics because it makes possible the relative motion of the overlying lithospheric plate. Now here, what I will do is, let me just have a new slide. And on this slide, is it visible to you? Hello?
Yes, sir.
Yes, sir.
Okay. Okay. So now what I will do is, so this is the earth, and on this earth, what happens is it tried to cool down from outside. Now, what has happened that when it was cooling down, this upper portion became more rigid and more solid. And because there was no volume decrease here, so it was unable to fit in itself, so it got break at many of the places. And because inside this it was hot, so the material came out of this. These breaks. Okay. Now, if the material is coming, then what happened? It will fall here. And after some time, it will cool down. Then the newer material will come. So it's like this. So the material has come and it has fallen here. After some time, again the newer material will come and this will push this. So in a way, there will be a thick plate here. Thick plate here which will be moving. So this was a kind of movement which took place in this. Okay. So there were plates, and then the seismicity. The earthquakes are happening like this. So it means that there are plates, and these are the boundaries of the plates. Now, the scientists, they worked out the plates like this. So there is a Pacific plate which is moving in this direction. There is an Indian plate which is moving in this direction. The Arabian plate is moving in this direction. And to our interest is this portion. Here we are sitting in India. So the Indian plate is moving in this direction, and this is the Himalayas. Okay, so Himalayas are still rising because the Indian plate is moving in this direction. Just let me introduce these boundaries also. So there may be divergent boundaries, there may be convergent boundaries, and there may be transform boundaries. Like this one, where the lava is coming out and it is pushing, they are known as divergent boundaries. Okay. Then the convergent boundaries, where the one plate is being going down and underneath the other plate, and this is the examples of the Himalayas. Okay, so in this case, this plate is moving, say around 2 centimeters per year. What will happen after 10 years? it will be moving 20 centimeters. And after 100 years, it will be moving 2 meters. Say after 400 years, it should have moved 8 meters. And you know that in a magnitude 8, the fault slip is around 8 meters. So it means that in 400 years, this plate accumulates such strains that a magnitude 8 may happen. And that's how we find the return periods of the earthquakes, deterministically. Then these are transform boundaries. And I'll just show you one of the Pangea and then how these things they move away from this. So here, if you see, okay, in this, if you see that these are the two continents, and people, geologists, they have found that the flora and fauna on these boundaries, the rocks on these boundaries, their ages and the edges, they just join like jigsaw puzzle. Okay, so therefore this plate tectonics, it shows that they have moved like this. Now, I'll take the case of India. 71 million a year ago, it was there. Then it moved towards the Eurasian plate, and last 10 million years, it is just colliding with this. And once it is colliding, then what will happen? That this portion where it is colliding, this plate is moving below the Eurasian plate. This is Eurasian plate, which is this one, and this is Indian plate. Okay, this is moving like this, and this plate is going down. Now, some of the material will ooze out here, and this material is known as Himalayas. So the Himalayas, they are formed because of this, and because it is just colliding here, so very intuitively I can tell that the earthquakes must have been occurring here. Now if I see the past earthquakes, largest past earthquake, I can see that they have all happened here itself. I don't know how this will go. Okay, go on. So, 1905 Kangra earthquake, Dharchula earthquake. Then this was this Bihar Nepal earthquake. This is again Bihar Nepal, Shillong earthquake, Assam earthquake, Kutch earthquake. They are all the earthquakes which were magnitude greater than 7.5. Now, I'll come to another aspect which I thought that it is necessary. Now, if the earthquake is happening here, so the waves are propagating in all directions. How far the wave can go, how that is propagating, and how that is creating the damage. So we must know the propagation of the waves. Now, once I consider that the earth is a elastic media, then it means that there are only two types of waves, body waves, which may happen. They are the primary and secondary waves. It is a 12th class theory, and you know that the compressive waves, the P waves are similar to sound waves, They obey all the physical laws of the science of acoustics. The mass particle motion of the P wave is in the direction of the propagation of the wave. Okay. In addition, P wave causes a momentary volume change in the material through which they pass, but no concomitant momentary shape. Okay. So if I see that how these primary waves, they propagate like this. Okay. So the particle motion is in the direction of the propagation, and it is the rare fraction and the compression and the dilatation. And this is how the primary waves, they move within the medium. The other waves are the S waves, the shear waves, the secondary waves, which move in a direction perpendicular to the direction of the particle motion. Okay, they do not change the instantaneous volume of the material through which they pass, but as they pass through material, they distort the instantaneous shape of the material. The geotechnical persons, they understand it very well. What is the importance of the shape change of the material, and how they propagate is like this. So either in the vertical direction or in the horizontal direction. Okay, so this is how the waves are moving. Now in earthquakes, you have another kind of waves, which are known as surface waves. Okay, I'll just tell you very simple form that if there is a boundary and if a P wave is coming here, the particle motion will be in this direction. Suppose at the same time the S wave has also come. Now the particle motion will be in this direction. So the particle will move as per the P and S both. And the resultant motion will be retrograde elliptical. And these are the waves which are very important in case of earthquakes. Because say if I make a seismogram, then the seismogram look like this. Here, these are the primary waves which have come first because they have the higher velocity. These are the secondary waves which have come next because of the lower velocity. And these are the surface waves. And if you can see the frequency also, the surface waves has got very less frequencies. They have got lesser, and the primary waves are having higher frequency. These are the relay waves, which now you can see the ground motion is along the surface only. If you see this and this, you will find that it is not changing. Only the upper portion is changing, and therefore they are known as surface waves. So when there is a vertical motion, they are known as relay waves, and when there is a horizontal motion, they are known as love waves. So both kinds of wave propagation is available. Now, you know the Earth. Inside the Earth, how you will know what material is there? There is no other way to put the energy into the Earth other than the earthquakes. So earthquakes are only responsible to know the internal structure of the Earth. So and that is also very important to know that the internal structure of the Earth is like this, that you have the crust part, which is less than 100 kilometers. Okay. Then you have the upper mantle, then you have the lower mantle coming up to 2900. Then you have the outer core, the inner core. Okay. And if you want to see this 700 portion here, then you will see that there is low velocity zone between 100 and 250, and then this low velocity zone is important from point of view of the plate tectonics. I've told you that this portion, lithosphere, is very rigid. And this is a low velocity layer. So here the rigidity is very less. So this is just floating above this. Okay, so this low velocity layer, which is part of the upper mantle here, this is giving you the motion of these plates, and because of which the earthquakes are happening. So if you want to see the absolute values of the velocities, then in the crust, the P waves, they have the velocities around 6 to 7 kilometer per second. Then, here, then it goes up to lower mantle at around 13 kilometer per second. Then outer core, it comes down 8 kilometer per second, and then it goes. So in inner core, we have the velocity of around 11 kilometers per second for P waves. This is the S wave, and here you will see there is a blank. Because the outer core is liquid, there is no movement of the surface waves because of their shear strength is not there. Okay. Now, how these waves are propagating inside the earth is like this. They can be reflected along the surface. So, so this is the source. From here, the P wave may come here. It may get reflected, PP may get reflected 3 times, PP. Those waves which are going up to the core and coming back, they are known as PCP. The one which are going inside the core and coming, they are known as PK, and it is reflected from here, IKP. So my aim here is not to tell you about these waves, but just that if there is earthquake, then the whole earth is energized, and in case of magnitude more than 8, the waves, they may propagate like this, and they may come back to the source after some time. And therefore, you may see the seismograms for hours and hours. And if the earth has gone into football mode, then the earth itself looks like taking breath. So sometimes the structure of the earth is like this, and sometimes the structure of the earth is like this. So it goes in those kinds of fundamental modes also, where they vibrate with this, and it is around 45 minutes or so, the period. So for 45 minutes, it is taking just like breath. So why I'm telling is because for the earthquakes, we know that a 5 magnitude earthquake or a 6 magnitude earthquake, but a 8 magnitude and a 9 magnitude earthquake, they have so much of energy that they can really energize the whole earth. Okay, I'm not going into this. These are some of the actual seismograms which I want to show to you. This is P wave, which is, this is the P wave, and somewhere here the S wave has come. Similarly here, the P wave, the S wave has come. So these are the actual seismograms recorded on this. The records are known as seismograms. While the recorder, which is recording it, is known as seismograph. Okay, similarly, if you are recording acceleration, then the record will be known as accelerogram. and the recorder will be known as accelegraph. So this is the difference between these two. Now, I'll just maybe I can skip this and directly come to some part of the seismological instrumentation, because you should know what kind of instrumentation is used. The instrumentation is based on the principle of inertia, because there is no reference frame, because the whole earth is moving, and therefore everything will be moving, and you cannot record anything on this. So we make use of the moment of inertia. Here in this, I want to show that if the frame is moved on this direction, the ball will not move because of its inertia. It's a heavy mass, and the difference between these two, the pillar and the ball, will give you the relative motion. So all the seismometers, all the accelerometers, everything which is recording the earth movement is based on the principle of law of inertia. Nothing else. Every instrumentation in seismology. Rest of it is, the electronics and how to record faithfully. Everything is after that. But the basic principle of recording the earthquakes is the law of inertia. Okay. Then basically the seismometers are designed to react to the motion of the earth in a given direction. Mechanical instruments record the amplified displacement of the ground. Electromagnetic instruments respond to the velocity and may respond to vertical or horizontal motion. Simultaneously record three horizontal components. I will be showing you some of the diagrams, how it is recorded, because you may be using seismograms or the seismograms, then you must know how they are recorded, and you better understand the ground motion in reality. First, let me introduce the first one. This was the first instrument which was constructed in 134 AD by this gentleman known as Chell. And in this, there are bars inside this. Okay, now these bars, they open. Like in this, it's arrangement like this. So if there is some motion, then this bar will move and it will open the mouth of this dragon, and the ball from here will fall down on the mouth of this toad. Okay, the frog. And because there was no record of this, nothing, it was just showing the direction and that the earthquake has come. Okay, so it was also known as some of them they have known as Bedonji. Okay, but scientifically we call such kind of instruments as seismoscope. This is a seismoscope which is not giving you no records, no timings. Only that some earthquake has come, that's it. But when we have recording and the timing, then we call this as seismograph. Okay, now I will be giving you the example and the arrangement of a vertical seismograph based on the principle what I have given you. There is a heavy mass here which is attached to this spring. So it means that this mass is detached from the system. Now, if there is any vertical motion, this mass, because it is detached from this system, this will not move, but the drum will move. Please try to understand this. The mass is not moving, the drum is moving along with this frame. Okay, and this pen is putting mark on this, and this drum is moving in this direction. Okay, so in case of some earthquake, this will be like this. Okay, so this kind of manual arrangements are made, but you know that the ground motion is very feeble. You are unable to record this, and once the motion is there, you have to have a permanent record of this. So we make use of the this magnet and coil arrangement. And if you remember the history of this solenoid, that gentleman, he made the solenoid, and for months he was doing something, and then in the last he threw the magnet inside the solenoid, and then he got it, and then he came to know that okay, this, it is not the displacement, but it is the velocity which is working. So here the main thing is that the output is in terms of velocity. Earlier in the manual and for other oscillograph types, they are all the displacement meters, and all the seismometers are basically velocity meters because of change of mechanical vibrations to electromagnetic this uh, signal. Okay, and once it is electromagnetically available to me, then what I can do is I can go for the amplification of this. That is much easier than for this. This is one of the horizontal seismographs. Here you make use of the just displacing the fulcrum like the refrigerator gate, and then this is free from the other things, and you can record the horizontal ground motion. But in this case, the thing is here I want to attract your invitation that here we are using a light source and this. Okay, so it means that by increasing the distance, I can increase the amplification also. This is a simple light source arrangement and light beam falling on this. So the more the distance, the more will be the amplification on this. So these are for the vibration parts. Then there is a zero frequency seismology also, where you want to know between the two pillars, what is the deformation or the displacement. So for that, you either you go for the quartz tube, these arrangements, or the tilt meters for the vertical arrangements. Okay, but in this more scientifically, what you have to do is you have to put the damping also. So the modern seismographs, they have the mass and the damping, and then it is a spring mass damper system. You can go for the equations, go for that, but you know that as per the mass spring system, the length of this, the weight of this, they will decide the frequency or the natural period. And you know that depending on the ground motion natural period and the natural period of this, you will have the resonance curve and you will be recording faithfully some of the motion. So, I mean, it means that the whole ground motion cannot be recorded by a single seismograph, but it has to be recorded by a combination of these two. Let me give you one example. This is one of the earthquakes. This is a single earthquake, and on this, what we have done is that on one platform we have placed 4 seismometers. Okay, having different characteristics. So the first one, the characteristic was this. It means that it was passing all these but rejecting all this. Okay, so only the high frequency around 10 to say 50 hertz, they were recorded. So the seismogram will look like this. Now here in this case, it is rejecting all the higher ones, but recording faithfully these ones. I mean 10 to the power -1 or -2, 0.00. So all the lower frequencies are recorded here. Here in this case, it is a broadband. It has recorded the higher ones also and the lower ones also. And here you will see that the lower frequency is also there and the higher frequency is also there. In this case, it has all recorded the lower ones but not the higher ones. So the seismogram looks like this. So what I want to show here is that a single earthquake is recorded by many seismometers of different characteristics, and therefore the amplitudes, these are different. So, and you know the magnitude is defined based on the amplitude. So it means that you have to have a common definition of the earthquake. And fortunately, this definition was given in 1935 by Richter based on the Wood-Anderson standard seismograph. So that Wood-Anderson standard seismographs look like this. This is a Wood-Anderson standard seismograph. Here there is a copper mass which is placed in the magnet to damp, so the eddy currents will be generated and it will dampen it. And then there is a light source which is coming from here. So there was a light source here and a recorder here. So the distance between these 2 points will give you some amplification. So the amplification is given by this, the damping is given by this, and based on the arrangement, a standard Wood-Anderson seismograph was made with a natural period of 0.2 seconds, damping point 80% of the critical, gain as 2800. Okay, and this was achieved by having a weight of cylinder as 0.7 gram, diameter. Please don't see this. I don't want to show this. Diameter as 2 mm and length as 2 meters. Okay, so based on this, Richter defined the magnitude. So the magnitude, first magnitude scale was defined by Richter 1935 for earthquakes in California using seismograms from earthquake recorded in South California. So what he did, he plotted all the magnitudes which were recorded here with log of peak of the amplitude on y-axis in mm and distance in this. So you see, if you see this magnitude 3, now one station at 50 kilometers it recorded 1 mm, another one at this lesser and lesser and lesser. So what he did, based on this, he defined the magnitude. A magnitude 0 earthquake as being that, I now please listen carefully, this one, a magnitude 0 earthquake as being that which theoretically produce a maximum trace or record of 1 micron on a seismogram from the then standard Wood-Anderson seismograph at 100 kilometers. Okay, so this was the first achievement by Richter towards the magnitude. Okay, based on this, he defined the magnitude as this. The magnitude is defined as the logarithm to base 10 of the largest trace amplitude measured in microns, that is 0.001 millimeter, on the record made by Wood-Anderson seismograph at a distance of 100 kilometers from the epicenter of the earthquake. It means that an earthquake producing a trace of 1 millimeter at 100 kilometer distance would be assigned a magnitude of 3. So a magnitude 3 means that on Wood-Anderson, if it is placed at 100 kilometers, the trace will have 1 mm as the amplitude. So the formula he gave was like this: ml equal to log of a at delta. At delta is the distance. So, and sigma L delta. And sigma L delta is nothing but the log of the amplitude or at that distance for a magnitude 0. Okay, so it means for magnitude 0, you have to extend it and find what magnitude 0 will give at different distances, and that has to be added or subtracted from this, because it is in 0.00s, so that will come as minus, so minus minus will become plus here. Okay, so for example, this at 100 kilometers, this is 3. So it means that log of 1 mm will be 0. And if you add this 3 to that, then the magnitude become 3. So it means that this is amplitude of magnitude 0 at 100 kilometers. So he has defined it for this. Now, you can define it for other body waves. So the extension was made for, say, body, because the earthquake record will have the P waves, the S waves, the surface wave. Then all these magnitude scales were defined in a similar way as of the Richter magnitude, and then they were projected on the Richter magnitude so that the magnitude remains the same. So this sigma MB, sigma B for MB and sigma S for MS. Now these will be just find out so that MS and MB, they become same as ML. So these tables are made, and then you can find the magnitudes based on the surface waves and all. One of the common, because many of the people, they ask, no, we don't want to go for that. We want just the formula. This is one of the formula for surface wave magnitude. Log of 10 AS by T. So AS is the maximum amplitude in millimeters, and T is the time period of that wave for which you have taken the amplitude, and then delta is the distance in degrees basically. So you can find the magnitude. Other magnitude scales are also there. Say duration magnitude. You find the duration, find project it for your area, and then try to find. So it means that if you have some magnitude already found in your area, then you find the MD for that based on the duration, and then do the regression analysis and try to find the A0 and A1, these coefficients. Or sometimes you have the these templates for you. Say you know the amplitude is 23, and you know the distance from where it is coming, by distance, the time s minus p, you multiply it by 8, and then you get the distance, and then you join these, you get the magnitude, which is in between this. So, but the problem is the same story that as that of the elephant. I mean, a group of blind men, they were just given the elephant, and they were asked to define the elephant. The one who touched the tail, he said that the elephant is just like a snake. The one who touched the feet, he said that okay, it's a cylindrical kind of thing. But the elephant is elephant. So same case is with the magnitude. The magnitude is magnitude. It remains the same, but it is different for P waves. It is different for S waves. So people, they think that it is a disadvantage. I'll say that it is not the disadvantage. You are getting the idea of the energy release in different frequency bands. So the magnitude has to be different. But the people, they want, okay, we don't want this jugglery. Just give us one single magnitude scale. And then this moment magnitude was given. Moment magnitude is nothing but a moment calculated at the source. So you have the distance, and what is the moment? Force into distance. So that is force into 2b, and then this is equated to the strain, and in this case the moment magnitude comes out to be mu ad, where mu is the shear modulus, a is the area, and d is the displacement on this, and therefore you can find the moment magnitude also, which is nowadays most of the time used by the seismologists and the engineers. Okay. Then the energy release. Energy release is nothing but log of E is 1.5 times of this, and this is given by this formula. And I will just give you the example of the magnitude. So in case of one magnitude going one scale above, the energy is multiplied by 30. Sorry, 30 times higher energy is there. It means that a magnitude 8 is equivalent to 30 magnitude 7, which is again equivalent to around 1000 magnitude 6, which is again equivalent to 30,000 magnitude 5. Why I am giving you this is because many times people say that a magnitude 8 may come, and then they say, okay, Uttarkashi or Chamoli and all these, they have come, so the energy is released. But my dear, magnitude 8 means 1000 magnitude 6. If there occurs 1000 numbers of Uttarkashi and Chamoli earthquake, then they will be releasing energy of magnitude equivalent to 8. So, I mean, this is something that you should understand. And similarly, the engineers sometimes say that, okay, for this building, you take magnitude 7. And then suddenly next one will come, okay, no. I don't think you should take 7. Increase it by 7.5. Oh, this is not 7 and 7.5. You have increased the load by 15 times. I mean, one should understand this, that there is hell of difference between magnitude 7 and 7.5. Just like your creatinine, just like your blood pressure. I mean, for blood pressure, you people will say that, okay, I am having 120 blood pressure. I am having 300 blood pressure. What do you mean by 300 blood pressure? You will die. But because you understand, and therefore you remain in the range. Yes, I have got around 80 to 120 only. You don't go out of the range. But here you are going out of the range. 7 and 7.5 is a lot of difference. So you have to be very careful. Now, one of the very important topics which remains is the intensity. Intensity is another measure which is a qualitative description of the effects of the earthquakes at a particular location. So the difference between intensity and magnitude is that if you have, say, a bulb here, this is a 40-watt bulb and it is giving you the light. Now, here, the lumens will be less. The intensity of the light is very less here, almost dark here. And here also it is dark. Okay, so it means that the intensity is decreasing in this direction. So intensity may be 7 here, it may be 6 here, it may be 5 here, anything. But the magnitude will remain same. The bulb will be of 40 watts. Okay, so the magnitude of an earthquake remains same. The intensity changes because it is the observation at that location. Rossi Farrell gave in 10 stages. So if it is a observation, then it has to be, in terms of the secondary effects, what is the effect on terrain, what is the effect on water, what is the effect on construction, loose objects, and miscellaneous. So all these, when they come together, then that make a intensity scale. So I will directly come to the intensity scale, which is of use to you people, and that is the MSK scale, which was adopted by UNESCO also in 1964, because it is based on the observations, and most of the intensity scales, they were having those kinds of things which were non-existent in the areas where the intensity scale was not made. So UNESCO just made this, and the terms were defined like the type of structure, A, B, C, building in field stone, rural structures. B, they are ordinary brick buildings. C are the reinforced buildings. Then the quantities were also defined. 5% means single or few. Many means about 50%. Most means about 75%. Then the grades, G1 to G5, from very slight damage to total damage. I'm not going into details, but they are going linearly. Okay. Now intensity 1, not noticeable. Scarcely noticeable. 3, weak, partially noticeable. So here you can do the interviews and assign the intensities. 4 or 5 even, there is, you can see that they are all based on the interviews, and no building environment has been taken into consideration. But when you start from 6, then you have the intensities based on the damages. These are the damages. Damage of grade 1, very fine, is sustained in single buildings, means less than 5%. Type B means brick masonry kind of thing. And in many, more than 50% of type A, kacha houses. Okay, so these intensity scales, they are defined like this. Suppose I go to intensity 8. Now here you will find that most means around 90%. Type C means reinforced. Grade 2 means little more than grade 1. I mean, little more cracks. And few of grade 3. Even much more wider cracks. Okay, so these intensity scales are to be understood from 3 points. One is that you have the interviews where there is no um, built environment is considered. Then you have the built environment, and in built environment, because it's before you, so you see what kind of building, how many numbers of those kinds of buildings, what kind of damage, which grade is there, and depending on that, you fit it in your intensity scale and assign the scale intensity that, okay, this will be 8. Then C is based on the terrain, because sometimes after some time, the built environment is totally damaged. There is nothing left, like in 9. Here, everything, many buildings type C, I mean, B and grade 4 and grade 5. So it means that this will go away. After some time, total damage will be there. And then you have to go to the terrain part. And then C part will come into picture. And you have to look for the evidences on the roads, on the wells, on the nature. More than 10 intensity, 10, 11, and 12, they are very specific and they have to be defined very, very carefully. Because you know that Bhuj earthquake, it reached up to 9 only. Very, very less number of earthquakes, they reached up to 9 or 10. There are only 1 or 2 examples. I'll just ask you to Google it. How many earthquakes have reached up to 12 intensity? So this is exercise for you to go for it. Okay. Then this is the details of modified MMI scale. So, I mean, how the similar scales they are given in different these things. So you can go for just matching of these. Now, a little bit time is left. So what I will do is I'll just cover some of the location part. Location is generally done by using the geometrical methods, just like you have the mobile with you. You know that the mobile will give you the location, latitude, longitude, and all that. So how that is given? Because you know the these 3 or 4 locations of the satellites, and based on that you make the normal equations, and then you go for this. So programs are available for this, and then you locate the earthquakes. Then the types of physically what is going on. So the fault, this is a fault plane. The plane from the horizontal, that is the dip angle, most of you know it. The slip angle is the angle where it is slipping, and the strike is at the surface. Okay, so based on whether it has slipped on this direction or opposite to it, or along the strike. So if it is if it is slipping along the strike, we call that as a strike slip. If it is slipping along the dip, we call that as dip slip. Okay, strike slip may be of 2 types. If it is like this, or if it is like this. Dip slip, maybe it is going up or going down. So based on the slip, we have the classifications. So a dip slip and a strike slip. So if it is slipping downwards, then it is a normal fault. Otherwise, it is a reverse fault. And they are just like this. This is a left lateral fault. Just you have to stand on one side and look at the other side. So the direction in which the other side is moving, that is the left lateral. Here you stand. This is moving on the right side. This is a right lifter. Here, the hanging wall. This is hanging wall. This is footwall. If the hanging wall is coming down, it is known as normal fault. If it is going up, it is known as reverse fault. Okay. Then these are the faults all along the Indian part, and then the earthquakes. This is a very old figure. I don't want to go for this. And then I come to the last slide. Now, based on all your knowledge of engineering seismology, what you do? What you do is you are supposed to calculate the seismic hazard. This can be done deterministically, this can be done probabilistically. So here deterministically, you go for the motions, or you just go for the ground motion prediction equations and try to find the seismic hazard. And the result of the seismic hazard is in terms of the prediction of probabilities of ground motion. Okay, what is the probability of accidents of a ground motion point 3 in your area? So that kind of result you have, and these results, they are used for earthquake resistant designs, they are used for seismic microzonation, they are used for retrofitting measures and all that. So what I have taught you is just the engineering seismology introduction. And based on this, you have some of the theories, and you find the seismic hazard assessment. These are separate topics. So I have just introduced the things to you so that you can now go for a study of seismic hazard, which will be a basic study which will be used for the further points. Thank you. Thank you very much. If there are any questions, I can take them.
Yes. Thank you, sir. Any question from participant side?
But if there are any questions, I will. My email is there. You can give the participants the email ID. They can send the questions, and I will address them.
Sure, sir. Yeah, thank you, sir. Thank you very much for very nice and very informative session. And your talk is always very informative and very interesting talk. Always, I enjoy it, and I hope all participate definitely get the benefit from this talk. You have touched on all the aspect from engineering seismology point of view, and uh, thank you very much, sir. And thank you, sir.
Thank you. Thank you. So I leave
Thank-
it.
Yes. Okay. Thank you very much, sir. Thank you, sir.
Thanks to all the participants for their hearing and calling. Thank you.
Yeah. Okay. All the participants are requested to fill their attendance on the chat box, link already shared, and all the participants are requested to come together 2:30 p.m. after 1 hour. After 2:30 a.m., the session talk from on introduction to earthquake engineering and overview. Okay, and we can again meet here 2:30 p.m. Thank you very much. Thank you.
Thank you, sir.